Hello friends, welcome back to my channel. So in today's video we will take rearrangement reactions as well as we will take fragmentation, how we can do fragmentation reactions. So in the last of the video I will take an example based on neighboring group participation in case of cis-nor-bronene type of compounds. So this is a request example, so I will take in the end of the video. So first we will take Pinacol rearrangement. Pinacol rearrangement is basically observed in 1,2-diols and we need acid for this reaction and it will rearranges to give us ketonic compounds. Right, for example this one is Pinacol, and when we will use a protonic acid in this reaction, this OH will first form OH2 plus. Right, in next step it will be removed and we will get here a tertiary carbocation. So this carbocation is stable in nature, but the better stabilization can be get when we have this positive charge close to this OH. Right, a heteroatom having lone pair of electron can better stabilize a positive charge than the stabilization by inductive effect. Right, so how this can be possible that we will get a positive charge here? If we migrate one of this methyl group to this position and we will get positive charge here. Now this oxygen having lone pair of electron can stabilize this positive charge and we will get this compound, this is pinacolone. So in this case we have two methyl groups, so any one of them can migrate, but if we have different type of alkyl groups attached, then preference will be given to electron rich migrating group. Right, because we want to stabilize this positive charge, that's why we will give preference to electron rich molecule. Then stereo of migrating group is retained, means if it is attached above the plane, then after migration it will remain above the plane, its stereo will remain as such. Right, so we will take such type of example in later cases. So next example is this one. Again we will do protonation of suppose one of these OH, because both of them are similar, so we can do protonation of any one of them. Right, so when this OH2 is removed we will get a positive charge here. Now we can stabilize this by migrating this carbon suppose. So when we will migrate it, this ring will become 6-membered ring and this carbon is attached with OH, now has positive charge, because after breakage of this bond it will get a positive charge, and now we can stabilize it by using this lone pair of electron and then proton will be removed. So finally we will get this molecule. In next case we have different type of group attached on these two OH. So we have to decide that after removal of H2O which cation form will be more stable. If I will remove a H2O from this carbon, then I will get a tertiary carbocation, and if I am removing OH from this carbon, then I will get a positive charge which is also tertiary carbocation, but this time it is stabilized by 2 phenyl rings. So this will be more stable in nature. That's why this OH will be protonated, and after removal of this we will get a positive charge on this carbon. Right, now this ring will migrate, and when it will migrate this ring will become 6-membered ring and we will get ketonic group attached here. Right, so you have to decide first which carbocation form will be more stable, then electron rich migrating group. Then we will take Semi-pinacol rearrangement. In case of Pinacol rearrangement we have synthesized carbocation which is more stable. We will do protonation of OH group which will form more stable carbocation. But in case of Semi-pinacol rearrangement we generally use tosyl chloride in presence of pyridine. So this tosyl chloride in presence of pyridine preferentially attached with OH which is less hindered. Right, so this OH is less hindered as compared to this one, that's why it will combine with this oxygen after removing this H. Right, so preference will be given to primary, then secondary, then tertiary in presence of tosyl chloride and pyridine. Right, now this tosylate is a good leaving group, and when it removes we will get positive charge here, and we can stabilize this positive charge by this oxygen having lone pair of electron, but before that we have to shift this positive charge from this carbon to this carbon. Only in that situation this oxygen can stabilize this positive charge. So we can migrate any of these two carbons because both of them are similar. So if I am migrating this bond will break, this will break, and after breakage of this bond we will get a ring which is 7 membered. This will remain as such, and on this carbon we have positive charge, right? Now this oxygen having lone pair of electron can stabilize this positive charge, and we can remove proton at this stage. We will get this molecule, right? In next case, again we are using this tosyl chloride and pyridine. So we have 2 OH group here. It is also a reaction which is applied on 1,2 diols. So we have 2 type of OH here. This one is less hindered as compared to this one, right? It is tertiary OH while it is secondary in nature. So this tosylation will be done preferentially to this. Now we have to shift this positive charge. When we remove this tosylate, we will get a positive charge here, and we have to shift this positive charge to this carbon. How we can shift it? If we will shift this bond, so we will get a 7-membered ring here. We have double bond here, and now we have this carbocation. So this oxygen can stabilize this positive charge. So I am directly writing here, first double bond here and positive charge on oxygen, then this H will be removed and we will get ketonic group attached here, right? Next type of modification can be possible in semi-pinacol rearrangement is that we are using silver nitrate and we are using I substituted compounds. Instead of 2 OH group, we have here 1 OH and 1 I. So this silver can attach with this I. Now it will become more desperate to leave this molecule, and when it will remove, we will get a positive charge here, and if we shift this bond here, we will get positive charge on this carbon, right? So this ring will become 5-membered ring, right? So we will get this one as final molecule. Then next modification can be possible that instead of OH we have NH2 group attached here, and we are using NaNO2 and HCl. So we can synthesize diazonium salt here. So we will get N2 here, right? So when this N2 is removed, because it is a good leaving group, we will get a positive charge on this carbon. So any of these 2 carbon can migrate, and if they will migrate, they will form a 8-membered ring, right? We will get this molecule. Next is Dienone-Phenol Rearrangement. So we have seen how we can do Pinacol rearrangement. This Dienone-Phenol Rearrangement is just opposite of Pinacol rearrangement. So first we have to protonate this oxygen, right? Now we can stabilize this oxygen by migration of this double bond, and to stabilize this double bond, this will migrate. So we will get a positive charge on this carbon, a carbocation, after shifting of this bond, and to stabilize this positive charge we have to migrate this methyl group, right? And we can migrate any of these 2 because they are same. So we will get a positive charge on this carbon, right? So in this case we are shifting methyl group and we are removing positive charge from this oxygen. So to stabilize this positive charge, a proton will be removed and we will get a double bond here. So we are synthesizing phenol here. That's why it is called Dienone-Phenol Rearrangement. So this is very simple example that we can migrate any of these 2 methyl group. But if we have 2 different groups attached here, then what will be the situation? So first we have to again generate this protonated oxygen, right? Then because of shifting of these bonds, we will get carbocation here, and to stabilize this carbocation we have to migrate either methyl or phenyl, and we know that phenyl can better stabilize as compared to methyl. So this will migrate here, we will get a positive charge on this carbon, and this proton will be removed and we will get, right? So it is easy to find out in this case that we can migrate this phenyl to stabilize this carbocation. But in this case we have 2 groups here. This is electron withdrawing group and it can stabilize a carbocation. So we can think that we we will migrate this phenyl to stabilize this carbocation, right? So if we are migrating phenyl, then what we will get, I am directly writing here, we will leave this carbocation with the electron withdrawing group, right? Because of shifting of this phenyl, we are getting an intermediate in which this positive charge is close to electron withdrawing group. Second possibility is if we are migrating this ester group, then we will get a carbocation like this. So out of these two, this one is more stable, right? That's why this ester group will migrate and we will get this type of. So in addition to migrating group, you have to also check that positive charge will be stabilized by which group. We are leaving this positive charge with which type of group, right? So it is also a very important thing. Then next is benzilic acid rearrangement. So this molecule, this diketonic molecule is called as benzil. And in this reaction, first we are using OH, then we are using acid. So this OH will first attack on this carbonyl, any of these two, because both of them are similar. So it will attack on this one. Suppose this bond will shift here, we will get this intermediate. Now this negative charge will come back to its position, and if it come back, then this carbon will become pentavalent. It will have 5 bonds, which is not possible. So this phenyl ring will migrate to this carbon and this bond will shift here, and when it will migrate, we will get this molecule. This is called benzilic. Next rearrangement is Favorskii rearrangement. We have seen benzilic rearrangement, right? So in case of benzilic rearrangement, we have diketonic compound, and in case of Favorskii rearrangement, we are replacing this ketonic group, suppose with this Cl. So the reaction mechanism will totally changed, and we can do this Favorskii rearrangement on alpha halo carbonyl. This rearrangement reaction is totally different from benzilic acid. So in this case, first we are using this methoxide, a base, which will remove a alpha proton. Next to this carbonyl, we have this alpha proton. So it will be removed first, and then we will get enolate, right? And when this negative charge will come back to its position, we will get negative charge on this carbon, which will attack on this carbon, and Cl will be removed. Because it is a good leaving group, it can easily remove. After shifting of this negative charge, we can remove it. So we will get a intermediate like this. We will do further reaction a little bit later. First we will see this alpha halocarbonyl. This is different from this one, but we will get same intermediate from this. How we can get this? The methoxide will first remove this alpha proton, and we will get a enolate here, right? And when this negative charge will come back, it will attack on this, then it will attack on this carbon, and Cl will be removed. So we will get the same intermediate in both cases. Next step is the attack of methoxide again on this carbonyl carbon. When it will attack on this double bond will shift on oxygen, right? Then this negative charge will come back to its position, and this bond will break. It will shift here, and the negative charge generated here will take proton from this methanol. So we will get ester, right? So in this reaction, we are getting esters from alpha halocarbonyls. Next we have one more example based on it. So first we are doing bromination of this ketonic acid, right? So how we can do its bromination? First we have to generate an enol, then that enol will attack on this Br, and we can do bromination at alpha position. So we will get alpha halocarbonyl. Now we can do Favorskii rearrangement. This base will first remove proton from this carbon. It will be removed, and we will generate an enolate here. Then this charge will come back. It will shift here, and we will get this type of intermediate, right? Now this methoxide will attack on this carbon again, carbonyl carbon. This bond will shift, and when it will come back, one of these bonds can break, and we will get this ester, right? In next case, we have a different type of alpha halocarbonyl in which we do not have any acidic proton. So this mechanism is different, and it is following benzilic acid rearrangement type pattern. That first this OH will attack on this carbon, this bond will shift here, then this negative charge will come back to its position, and when it comes back, this phenyl ring will migrate to this carbon and this Cl will be removed, right? So we will get this molecule. So the mechanism is little bit different when we are using a molecule in which there is no alpha hydrogen, right? So it is an important example. Then we will take Baeyer-Villiger rearrangement. So in case of Baeyer-Villiger rearrangement, we are synthesizing esters from ketones, right? So we are using per acid here. So this per acid will provide me a nucleophilic oxygen. This oxygen is rich in electron, so it will attack on this carbon and this bond will shift here, right? And then when this negative charge will come back to its position, any of these two bonds will attack on this oxygen because it is electron deficient in nature after removal of this carboxylate, because it is a good leaving group, and when it removes, this oxygen will become electron deficient. So this carbon will rearrange here to stabilize this. So we will get a 7-membered ring, right? So how we can decide that which group will migrate? Because this oxygen will become electron deficient after removal of this carboxylate, it is electron deficient in nature. So we need a alkyl group which is electron rich, which can better stabilize a cation. So first preference will be given to tertiary alkyl groups, then secondary, then phenyl ring, then ethyl, and least preference to methyl, right? So in this case, we are using first H2O2, right? And this H2O2 will attack on this carbonyl carbon, this bond will shift, and when it will come back, we have to migrate either this carbon, this methyl group, or we have to migrate this ring. This ring can better stabilize than methyl group, that's why we will migrate it, and when we will migrate it, we will get oxygen inserted in between this carbon and phenyl ring. Next case is unsaturated ketones. So in case of unsaturated ketones, we have a double bond as well as ketonic group, right? And if we are using a per acid like MCPBA or other per acids, they can do Baeyer-Villiger reaction as well as they can do epoxidation. We know that they can do epoxidation of this double bond also. So how we will decide that which will be done preferentially? So generally epoxidation get more preference than Baeyer-Villiger reaction. But second important thing is we have to decide this, that either this ketonic group is more electrophilic. If this ketonic group is more electrophilic in nature, then Baeyer-Villiger reaction will be done preferentially. We have to decide that this carbonyl group is more electrophilic in nature than the nucleophilic nature of this double bond. Epoxidation is due to the nucleophilic nature of this double bond, and Baeyer-Villiger reaction is due to electrophilic nature of this carbonyl carbon, because first step is the attack of this electron rich oxygen on this electrophilic carbon. So if our carbonyl group is more electrophilic than this double bond, then the nucleophilic nature of this double bond, then Baeyer-Villiger reaction will get more preference. And if this double bond is more nucleophilic than this carbonyl carbon, then epoxidation will get more preference, right? So in this case, we cannot decide that this double bond is more nucleophilic or this ketonic group is more electrophilic in nature, because there is no substitution here. But we can see that due to this cis arrangement of this benzyl ring, the epoxidation process is hindered, right? And we can easily do Baeyer-Villiger reaction. And in Baeyer-Villiger reaction, we have to decide that we have to migrate this secondary alkyl group or this tertiary alkyl group. If we will migrate this secondary alkyl group, then we will get oxygen inserted between this carbon and this carbonyl group, right? Because when we are migrating, then we will get oxygen inserted between that carbonyl group and between the migrating group, right? So we have to insert oxygen here. And if we are migrating this tertiary alkyl group, then we have to insert oxygen in between tertiary alkyl group and carbonyl, right? And we know that because migration of this tertiary group is more preferential, that's why we will get this molecule, right? In next case, first we are doing 2+2 cycloaddition reaction. So in first case we will get this molecule. We are synthesizing a 4-membered ring here. Then we are using zinc. So this zinc will remove these two Cl. We will get this molecule, unsaturated ketone. So we know that this 4-membered ring is highly strained in nature and it want to release its strain. And how we can release its strain? When we are using a per acid, that we can do Beer-Villiger reaction. And if we are doing Beer-Villiger reaction, we will insert a oxygen in between this carbonyl or alkyl group, right? So this ring will become a 5-membered ring. Secondly, we have here alkene also. So this alkene is also reactive in nature. So if we are using any other per acid like MCPBA or any other as per acid, then epoxidation can also be possible. But this H2O2 preferentially epoxidize only those double bonds which are electron deficient, because H2O2 provide electrons due to formation of this one, right? And this is electron rich in nature, so it preferentially attacks double bond which are electron deficient in nature. But this double bond is not attached with any other group which can decrease electron density over it. So if we want to do only Beer-Villiger reaction, we can use H2O2. It is very good reagent for that type of reaction. So it will not affect this double bond. It will remain as such. Next question comes, this carbon will migrate or this will migrate? This will migrate because it is tertiary in nature. So we will get this molecule, right? The next important thing is about stereochemistry. So stereochemistry is retained during migration. So if we are doing Beer-Villiger reaction over this ketone, then this group will migrate in preference to this methyl group. This ring will migrate because this carbon is secondary in nature, right? So when it will migrate, we will get oxygen inserted here, and the stereochemistry of this migrating group will remain as such. We have two groups, that this is secondary carbon and this is methyl, right? So out of these two, this secondary will migrate in preference to methyl group and we will get this molecule, and the stereo of this migrating group will remain as such. And this is a general rule that for all 1,2 type of migratory reactions, stereochemistry of migrating group, it will remain as such. Then next very important thing is stereochemistry of all rearrangement reaction is very important. So we are taking here an example of Semi-pinacol rearrangement, and it is for all 1,2 type of rearrangement reaction that we have to check stereochemistry of migrating group. So in this type of reaction, we have seen that when we have NH2 here and we are using NaNO2 in presence of HCl, then it will form diazonium salt. It is like this, and this nitrogen will become a very good leaving group. So when this leaving group is removed, we will get a carbocation here. And always remember that this migration of groups should be anti-periplanar. Means if we are migrating this group, we are removing this N2, we will get carbocation here. So we have to stabilize this carbocation by this oxygen, because it can better stabilize this carbocation. And if we want to shift this carbocation from this carbon to this one, then we have to migrate carbon atoms, right? We have to migrate this carbon. So when we will migrate it, we will get positive charge here, right? And migration of this bond is very easy because these two are anti-periplanar to each other. So we can easily migrate this carbon and we will get a 5-membered ring here. Now this positive charge can be stabilized with this oxygen and we will get CHO group attached here, right? So we will get finally a 5-membered ring. Suppose this is R, this will be final product. So why these two anti-periplanar group, this migrating group and this leaving group should be anti-periplanar to each other? Because if we are migrating this, if we are removing this nitrogen, then we can get electrons from this migrating group in anti-bonding orbital of this carbon nitrogen. So we are getting electrons from sigma to sigma star. From this sigma bond, we are getting electrons in sigma star of this carbon and nitrogen. So these two orbitals should better overlap, and for their better overlapping, they should be anti-periplanar to each other, right? Next, you can understand it by more examples. So in this case, we have OH arranged. One OH is axially placed and NH2 is equatorially placed. In our case, both are equatorially placed. In this case, they are cis to each other, right? So in next, again we have N2 generated here after this reaction, and when this will be removed, we need a alkyl group or a group which should be anti-periplanar to this bond, right? Only possibility is again similar to this one, so we will get again same molecule. Result will be same in both cases, right? In next case, we have now this NH2 placed axially and this is equatorially. So we need a migrating group which is anti-periplanar to this carbon nitrogen bond, and in this case, this bond cannot be anti-periplanar to this. So only possibility is we have hydrogen here which can migrate. So we have a situation like this. So this carbon hydrogen bond will break, it will shift here, and this hydrogen will shift here, and N2 will remove. This carbocation is stabilized by this hydrogen, so we will get a positive charge on this carbon. Now oxygen can stabilize it, so we will get this molecule, right? In next example, we have again this NH2 axially placed and this OH is axially placed, right? These two groups are anti-periplanar to each other. So after formation of diazonium salt, we will get N2 here. Now this oxygen having lone pair of electron can stabilize this carbon and it will form a epoxide here, right? So we have this molecule. So it is very important that these two bonds, the leaving group and the migrating group, should be anti-periplanar to each other. Next is Beckmann rearrangement. It is very important reaction. So this reaction is possible over oximes and we are using acid for this reaction. So for this reaction we can use protonic acid as well as we can use other type of acid like PCl5, SOCl2, right? And this reaction can be possible over cyclic as well as acyclic oximes, and they will give us amides. First we will take an example based on cyclic oxime. So first this H2SO4 will provide me a H+, it will combine with this OH. Now this OH2 is a good leaving group, it tries to remove from this molecule and we will get positive charge over this nitrogen, right? So we want to stabilize it, so we will shift this bond here. This alkyl group will stabilize this carbon, this nitrogen, we will get a 7-membered ring. So when we break this bond, this carbon will become electron deficient in nature, right? So we have positive charge here and water released at this stage will attack on this carbon and it will tautomerize to form amine, right? Next we have an example based on acyclic oxime, and the reaction mechanism of this acyclic oxime is little bit different from this cyclic one. First step is similar, that we have to protonate this OH, it will form OH2 plus, and if we will remove it, this migrating group will migrate and it will stabilize this nitrogen, and the lone pair of electron present on this nitrogen will shift here to stabilize this carbon. Only this step is different. So we will get positive charge over nitrogen, then this water will attack on this carbon and this bond will shift on nitrogen, which will tautomerize to form, right? So the very important question is which group will migrate. We have seen in previous rearrangement reactions that when we have an electron deficient center, mostly we have electron deficient center, so we have to migrate electron rich group which can stabilize that electron deficient center. But in case of Beckmann rearrangement, concept is totally different. We have to migrate the group which is trans to this OH. We are migrating this alkyl group which is trans to this bond, right? So this concept is very, very important. We have to remember this. We have to migrate trans groups. For example, in this case, first we are using this hydroxylamine, so it will form oxim with this carbonyl group. We have two possibilities, that we can form trans oxim or we can form cis oxim, right? This is trans, and the amount of this trans is greater than cis. It is more stable as compared to cis oxim, right? And if we are doing Beckmann rearrangement over trans, suppose this is 1, and if we are doing Beckmann rearrangement using this first oxim, then this group which is trans to this OH will migrate preferentially, and it will migrate to attach with this nitrogen, and we will get this molecule. And if we are using this cis oxim, second one, then we will migrate this methyl group which is trans to this OH, so we will get this amide. Next case is when we have tosylate group attached here. Instead of OH, we have tosylate attached here, and this molecule can rapidly convert into this trans form, and it is the interconversion is much faster than rearrangement reactions, right? So it is difficult to decide that which group will migrate, because this molecule is rapidly interconverting between cis and trans. So if such type of situation is there, then you have to migrate a group which can better stabilize the positive charge. Means this N-propyl group can better stabilize the positive charge than methyl. So it will preferentially migrate. So we will get this molecule. Then we have Beckmann fragmentation. We have seen Beckmann rearrangement reaction. Next one is Beckmann fragmentation reaction. So first we are using this hydroxylamine. It will form oxim, and it preferentially forms trans oxim in higher amount, right? Then we are using this acyl chloride, right? Next step is the shifting of this bond, because this acetate is a good leaving group, so when it will remove, we will get triple bond at this situation. So we have to break this bond to stabilize this nitrogen. So when we will break this bond, we will get a positive charge on this carbon, right? And I can also write it like this. So to stabilize this positive charge, this bond will break and we will get double bond here. This is very, very important example. So we have seen that how we can break a very stable carbon-carbon bond to stabilize this nitrogen, and how we can decide that which carbon bond will break, because we can also break this carbon-carbon bond, but we are breaking this one. So how we can decide that which bond will break, and under what conditions fragmentations can be possible. So we have to go in more detail of fragmentation. For example, in this case we are using a protonic acid. So this protonic acid can protonate any of these two OH. Suppose we are protonating this one, and when we are protonating this one, this water H2O plus will form, and it is very good leaving group. So it tries to go from this molecule, right? And it is taking some electrons from this bond, and it is going away from this molecule. So we have a sink here. Sink means which is taking electrons from this molecule, and we need a source also which can give electrons to this molecule. We have a source, that we have oxygen which can give electrons to this molecule, right? So we cannot break simple carbon-carbon bond, right? Because it is not polarized in nature. It is a bond between two equal types of atoms, so there is no polarization in this bond. We can easily break this bond, OH bond, because we have polarization over here, right? So we can break this bond easily. But to break carbon-carbon bond, we need a polarization in a molecule, and polarization can be possible when we have a source and sink. Source of electron which can give electrons to a molecule and create a negative charge over it, and a sink which can remove electrons from it and create a positive charge over it. So when this OH2 is removed, this O will give its electron to this bond, and this bond will shift here to stabilize this carbon, because after shifting of this bond, this carbon will become electron deficient, and to stabilize this bond will shift here. So we will get a double bond on this carbon. Next step is shifting of this bond, and we will get this molecule, right? So fragmentation is possible under these conditions only. In next example, again we are using a protonic acid, so it will protonate this carbonyl group, right? It will become electron deficient. This oxygen will become electron deficient, means it is acting as a sink. It tries to remove electron from this double bond, and we have a group attached here, methoxy group, having lone pair of electron. It can stabilize this double bond, it can stabilize this electron deficiency. It will give its electron to this bond will shift here, right? So it can stabilize this positive charge generated here. So this ring will become a 7-membered ring, right? In next case we are using OH here. So this OH will first attack on this carbonyl group. This bond will shift here, right? And when it will come back, this bond will fragment and mesylate group will be removed. So how this reaction is possible, how this fragmentation is possible? Because we have a good leaving group here. This mesylate is a good leaving group, and if it leaves, then we have a positive charge, and to stabilize this positive charge, this oxygen is giving electrons to this bond, and then this bond will shift here to form a double bond here, right? We will get this molecule. Then next is fragmentations are also controlled by stereochemistry. So we have seen that under what conditions fragmentations are possible. Next question comes that which bond will fragment, and it is a very good example based on this fragmentation stereochemistry. So first example is we have cis group attached here. These two groups are cis to each other, so we will try to write down them in chair form. So if they are cis to each other at 1,3 position, then they will become axially placed or equatorially placed. So we will form a more stable form, that is they are to avoid diaxial interaction. So in this reaction, when this tosylate is removed, this is the sink which is taking electrons away from this molecule. We need a sink, we need a source also. So this nitrogen having lone pair of electron will act as a source. It will give its electron to this bond. Now we can shift this bond here, right? So we will get double bond here, and this fragmentation can stabilize this carbon. After removal of this tosylate, we have a carbocation here which can be stabilized by fragmentation of this bond, right? So important thing is this bond which is going to be fragment and this bond which is attached with our leaving group, these two should be anti-periplanar to each other. The bond which is going to be under fragmentation and this leaving group bond should be anti-periplanar to each other. We are not talking about the anti-periplanar nature of leaving group and this source. We are not talking about this. We are talking about the bond which is going to be under fragmentation and this leaving group bond. So when it will break, we will get this molecule, right? And then we are using hydrolysis. So we will remove this imine and we will get ketonic group attached. We can write it like, next example is we are using trans. These two groups are trans to each other. So we have two possibilities here, that suppose when they are trans to each other means they will be axially equatorially or equatorially axially placed, right? So first suppose I have the situation where this NMe2 group is equatorially placed and this tosylate is axially placed. Other possibility is this NMe2 is axially placed and this tosylate is equatorially placed, right? We have two possibilities, but out of these two, this first form is more stable because it has less severe 1,3 diaxial interaction as compared to this one. It has more diaxial interaction. Diaxial interaction based on the nature of this group attached here. So this form is more stable and if this bond leaves this molecule, it is acting as a leaving group, and when it leaves, we need a carbon-carbon bond which is anti-periplanar to this, right? And because this is acting as a sink and this nitrogen can provide electrons, so in previous example we have seen that this bond fragments and this tosylate is removed. But in this situation, this bond is not anti-periplanar to this leaving group bond. These two are not anti-periplanar to each other, so it is not possible. So this type of fragmentation is not possible in this case, right? Only possibility is that we can have E2 elimination type reaction, that this bond will break and this tosylate is removed, so we will get this molecule. Or another possibility is that we have hydrogen which is also periplanar to this tosylate, so we can break this bond and this tosylate is removed. So we have only under this situation when this tosylate is axially placed and it is equatorially. In this situation, which is less favorable, means we will get less amount of this type of configuration, we can do this fragmentation reaction. How it is possible? That when this nitrogen will provide electrons to this bond can break because this bond is anti-periplanar to this bond, right? So it can break and we can get fragmentation product, means we will get a product similar to this one, but the amount of this product is much lesser as compared to this one. This one is much higher as compared to this product, because this form is less favorable. That is why the fragmentation is also less favorable for this molecule. We have seen from this example that the bond which is attached with leaving group and the bond which is going under fragmentation should be anti-periplanar to each other. Next is ring expansion can also be possible with fragmentation, right? So we have this example here in which we have this leaving group which will act as a sink, and this OH will act as a source, right? But this decaline molecule can exist in cis form and trans form. And why we are considering cis and trans form? Why we are not directly doing this reaction? Because we have to consider stereochemistry also during fragmentation, right? So first we will take trans decaline. This is trans decaline, right? And we have two possibilities, that this tosylate group, we have OH attached here, and this tosylate group is equatorially placed, or it can be possible that it is axially placed. So axial position is this one, and if it is equatorially placed, we will write it like this. So we are using a base here. This base will remove proton from this OH and it will form O minus, right? So when this O minus come to this place, this bond can fragment and this tosylate should be removed. But we know that these two should be anti-periplanar to each other. But in this situation, suppose this is like this and this bond is going downward side. So the sigma bond of this carbon-carbon sigma bond cannot overlap properly with this sigma star orbital of this tosylate, right? So they are not anti-periplanar to each other, so this reaction cannot be possible in this case. Fragmentation cannot be possible when this tosylate group is axially placed. Second possibility is when this tosylate is equatorially placed. So when this negative charge will shift here, this bond can shift and this tosylate is removed. So this leaving group bond and this bond which is going under fragmentation, these two are anti-periplanar to each other, right? So this bond can easily fragment and we will get this molecule. So it is better to first write in chair form, then we will try to write it down in planar form. So in this situation we have a double bond which is trans in nature, right? So we can write down it like this. It is trans in nature and it should be at 5-6 position of this CO. So it is 1 2 3 4 5 6 position, and it is trans in nature, right? So we will get this product when we have cis decaline and it is this tosylate is arranged like this. Trans decaline can have two type of diastereomer. This cannot show fragmentation reaction, it can show, and it will give us trans double bond here. Second possibility is that we have cis decaline. So we can have two type of structure of cis decaline. Cis decaline means one, because this other cyclohexane ring is attached at 1 2 position, and if it is cis in nature, then one bond should go axially and other will go equatorially. Suppose this one is going axially, this will go equatorial. Now I can draw a second ring here, right? And we have O minus attached here, and we have tosylate at this position, right? So if we are shifting this bond will shift here, and this tosylate is removed. So these two bonds, this one and this one, are anti-periplanar to each other. If we are placing this tosylate in axial direction, then this fragmentation reaction cannot be possible, but under equatorial position it can give me fragmentation product. So we will get a product like this. So again this double bond is trans in nature, right? So this is also, it will also give same type of product. Second possibility is we are doing ring flipping of it, and then we will form another type of cis decaline. So suppose one bond is going axial, other will go equatorial. So we have here, because this carbon-carbon bond is axial in nature, so O minus will go equatorial in nature. Then tosylate can be attached in two ways. Either we can attach it axially or we can attach it equatorially. In axial form it cannot show fragmentation reaction, again the same problem, the bond should be anti-periplanar. So under this condition it can show fragmentation reaction. This charge will shift here, this bond will shift here, and this tosylate is removed. So these two bonds, this bond and this bond, these two are anti-periplanar in nature, so we can do fragmentation reaction. And under this condition we are getting double bond here, right? So it is a double bond which is cis in nature, means it should be here, this is cis position, and we have carbonyl group attached here, so it will give me this type of molecule. So it is very important to determine the orientation of this ring before doing fragmentation, right? Under only that condition you can get correct position of double bonds. Then we will take Eschenmoser fragmentation reaction. So first we are using H2O2 here, then we are using tosyl hydrazine. So this tosyl hydrazine will, first this H2O2 will epoxidize this double bond, then this hydrazine will form hydrazone with this ketonic group. The next step is this nitrogen having lone pair of electron will provide electrons to this nitrogen-nitrogen bond, right? Then this double bond will shift here and this bond will break. This epoxide ring is already very strained in nature, so it will break. We will get this molecule, then this negative charge will come back to its position, then this bond will break. We can break this bond, it will give me nitrogen here, right? So this fragmentation is possible because we have a source of electron and we have a good leaving group also. So we will get a triple bond at this position and this ring will become larger in size, right? So it is also a very important fragmentation reaction. Then I will take a question based on previous video, that the question was that neighboring group participation is possible in cis norbornene type of molecule or not, right? So I have a example based on this. In previous case we have seen that we have this type of molecule and we can stabilize this bond by this pi bond. This pi bond shifts here and it can stabilize this carbon, right? We have seen in previous video that it is the case of neighboring group participation that we will get a carbocation like this, and in next case this acetic acid attacks on it and we can shift this bond, right? So this was the example where we have seen the NGP character of pi bond. But in this case we have taken only this norbornene molecule which is trans in nature. This acetate group is attached in trans orientation. So the question was if it is possible that we have a group attached in cis position, right? So it is this NGP, and we have seen that NGP neighboring group participation increases the rate of reaction. Why we are doing NGP? Because it increases the rate of reaction and it is more feasible than normal SN1 and SN2 reactions. So if we have this group attached in cis position, and in this case we have no double bond in this situation, then rate of acetylysis is much faster, much faster than without this double bond. Means in this case neighboring group participation is possible. That's why it is increasing the rate of this reaction. So how this reaction is possible? This brosylate group will be removed and we have carbocation here. Now this carbocation can be stabilized by this double bond. So here comes the role of this pi bond as a neighboring group, right? Again, if we are using a acetic acid, then it attacks on it and this bond will shift here and we will get a molecule like this. So yes, it is possible that when we have a group in cis position of norbornene molecule, then they can also undergo NGP, means double bond can show NGP character when we have group attached in cis situation, right? So I hope this video is helpful to you. If you like my videos, please share my videos with your friends and subscribe to my channel. Thank you so much for watching.